Now let's talk about group fairness in committee selection. The work is a joint work with Cheng and Kamesh Munagala from Duke and Zhihao Jiang from Tsinghua University. So the problem is about committee selection. It's also known as multi-winner election. So we are given N voters forming the set V and M candidates forming the set C. And our goal is to output a committee of sets K, where K is a given constant from the candidates. Committee selection problem have many applications. For example, we may select a parliament from people, and we may want to hire a group of people during the hiring process. Or it's also used in computer systems. So for example, a program may want to put some data into the cache, but the cache can only, for example, hold K bits of data. And there are many programs. So we need a process to select the data that we want to put into the cache. And in this paper, we consider the following two preference models. The first is the approval set model, where each voter either likes or dislikes a candidate. And her utility on a committee is the number of candidates that she likes in the committee. And there's also the ranking model, where each voter first ranks all the candidates, and then she ranks the committees by the best candidate in each committee. And let's look at an example. So there are 3 candidates, and some friends are going to play some sports during the weekend. And for example, let's say K equals 2, so for this time they have time to play 2 sports. And the first person has preference of the first kind. So his preference is of approval set. He likes playing table tennis and soccer, but he doesn't like playing basketball. And there's a second person whose preference is of the ranking model. And he likes playing soccer the best, and basketball the second best, and table tennis the least. So let's consider the following 2 committees. The first committee is soccer ball and table tennis. The second is basketball and soccer. So for the first person, because he likes 2 candidates in the first committee, but only 1 candidate in the second committee, he will prefer the first to the second. And for the second person, because his favorite candidate in the first committee is soccer, and his favorite candidate in the second committee is also soccer. So by our definition, he is indifferent between the 2 committees. And we want the committee selection process to be fair. So by which we mean every demographic of voters should feel that they have been fairly represented. So more precisely, they shouldn't have the incentive to deviate and choose their own smaller committee, which gives all of them higher utility. And we consider a setting where we don't know the demographic slices. So we require the notion holds for all subsets of voters. And the notion here dates back to the 19th century and have received significant attention. For example, the notion of core and linear equilibrium are all based on this idea. So let's formally define this stable committee. Given 2 committees, S1 and S2, we say the capture count of S2 over S1 is the number of voters who strictly prefer S2 to S1. And we write V S1, S2 to denote that. And given a committee of sets K, we say another committee S prime blocks S if the fraction of voters who thinks S prime is better than S is at least the relative size of S prime and S. So for example, if the size of S prime is half of the size of S, then we need half of the voters who thinks S prime is better than S in order for this inequality to hold. Or equivalently is that formula. And we say a committee is stable if there is no blocking S prime. Let's look at a figure. So here is the set of voters. And for example, they elected the committee here. So there is a smaller potential coalition in the voters. And they may potentially elect another committee. So if all of the voters here think the smaller committee is better than the original committee, then they will deviate. And in that case, we say the larger committee is unstable. So because the smaller coalition only has smaller power, the committee that the coalition elected is of proportionally smaller size. And the notion here has some desirable properties. So here is the fair taxation interpretation. So each voter pays K over N tax towards buying any committee member, and each committee member costs $1. And for any coalition, because it has smaller number of people, it can only buy a smaller committee. And if a committee is stable, then no coalition of voters can spend their own tax money to build a better committee for all of them. So their complaints are not justified. Now, it's natural to ask whether a stable committee always exists. So unfortunately, for the approval set setting, we still don't know whether a stable committee always exists. But we can show that in the ranking setting, it's not the case that stable committee always exist. So let's look at a counterexample. So in this example, there are 6 voters from 1 to 6, and there are 6 candidates from A to F. And say we are allowed to select a candidate, a committee of 3 candidates. And here are the first 3 voters. Voter 1 thinks A is the best candidate, and B is the second best candidate. And voter 2 thinks B is the best, and C is the second best. And voter 3 thinks C is the best, and A is the second best. So it's cyclically symmetric. And 4, 5, and 6 are similar. It's 4 thinks D is best, and E is second best. 5 thinks E is best, and F is second best. And 6 thinks F is best, and D is second best. So we look at the first 2 voters. They both kind of like the candidate B. So we can say A or B must be chosen in any stable committee, or otherwise voter 1 and voter 2 will form a coalition and elect B instead. So because 6 voters can choose 3 candidates, we know 2 voters can choose 1 candidate. They have enough money to choose 1 candidate. So we conclude that A or B must be chosen. And because it's cyclically symmetric, we can also say B or C must be chosen, or otherwise 2 and 3 will form a coalition and deviate. And also C or A must be chosen in any stable committee. So we conclude that at least 2 out of A, B, C must be chosen in any stable committee. And because 4, 5, 6 are similar, we know any stable committee also has at least 2 out of D, E, and F. So any stable committee must have sets at least 4, but K is only 3, so we know there's no stable committee here. So to bypass the difficulty, we define the notion of stable lotteries, which is a randomized stable committee. So we say a distribution delta over committees of sets K is stable if for all other committees S prime. In expectation, the number of voters who think S prime is better than S is less than the proportional number, the size of S prime over the size of S times N. So this is our definition of a stable lottery. So we want to ask whether a stable lottery always exists. So here is our main theorem. So in the approval set setting and ranking setting, a stable lottery always exists. So this is our formal theorem. So we can think of our selected committee as the defending committee, and the coalition will form an attacking committee. So we will choose a distribution over defending committees, mean over delta D, and the attacker will choose an attacking committee, max over SA, so that in expectation, the number of people who thinks the attacking committee is better is not of a large enough size. And we can view this thing as a zero-sum game. So we can swap the max and min here. They are equivalent. So our goal is to prove this. Let the coalition first give a distribution of attacking committees. And then we look at the attacking committees. We will design a way to choose a defending committee so that the number of people who think the attacking committee is better is not too many. So given an attacker strategy delta A, we define B to be the relative size of SA and the size of SD. So we will rewrite the thing above to be this. It's just we change the SA over K to be B. And our strategy is this. If a candidate is chosen with probability PC in the attacking distribution delta A, then we select C into the defending distribution with probability PC over B, where B is a constant smaller than 1, so we are scaling up the probabilities. And we will use randomized dependent rounding to ensure that the defending committee that we select never exceeds the size K. And here is the thing that we want to prove. So in the proof, we need a probability matching lemma, where let YCs follow the Bernoulli distribution. So YC equals 1 with probability PC, and equals 0 with probability 1 minus PC. The YCs denote the attacking distributions. And YC equals 1 if a candidate C is chosen in the attacking lottery delta A. And the YCs can be arbitrarily correlated. And we define this as XC to be the scaled up version. So XC equals 1 with probability PC over B, and XC equals 0 with probability 1 minus PC over B. And we say that since the XCs are formed by the rounding procedure, they can't be arbitrarily correlated. So here we say they are independent of Y, and they are independent of each other. And XC equals 1 if C is chosen in the defending distribution. And our claim is the probability that the sum of YC greater than the sum of XC is less than B. So we need a new variant of the Chernoff bounds for integer valued deviations. And the probability inequality here nearly implies the inequality above for the approval set setting. Okay, so there are still some open questions in this problem. So first, it's still open that whether a deterministic stable committee always exists in the approval set setting. And also, it's open that whether a stable lottery always exists in the additive setting, where each voter has a utility for each candidate, and his utility for a committee is the sum of the individual utilities. And also, it's open that can we compute the stable lotteries efficiently. So what we can do is that we can compute an approximately stable lottery in the ranking setting, and we can compute an approximately stable lottery in the approval set setting when k is a constant. So for the more general settings, it's still open that whether we can do that efficiently. So that's all I have. Thanks.